In this episode, selecting the right plants for your bioretention system. Stories about water and urban places. This is Ideanthro. Hey everyone, and welcome back to Ideanthro. It has been a while since I have made a new video here. The reason for that is that I've actually been off pursuing another interest of mine, human movement, by running a very different, a very unique little gym of sorts. You can find out more about that at ideanthromovement.com. But we're here today to talk about water, and specifically how to select the right plants for my bioretention system. Now, what's drawn me back into talking about water after having a bit of a break from this space is a really interesting conversation with three people, Ben, Craig and Andrew from Blacktown City Council. We've been having this chat over email and I can't help but talk about this stuff. And anyway, out of that conversation came an idea in my mind about a little framework here for how to pick the right mix of plants for a bioretention system. So I want to say thanks to those three guys for a really great conversation that has kind of spurred this in my mind. This isn't meant to imply either way that they agree with or endorse this or not, but I did want to give my thanks to the three of them for the conversation that has led to me putting this together and drawing me out of my, my video hibernation. So this is going to be a little thought process for not necessarily the individual species, although if you followed this through, it would then put you in a good position to pick the individual species for your bioretention system, but I'm not going exactly there because that will depend on your particular geographic location and site-specific factors and whatnot. But this is a thought process to get you to the right mix, the right types, the right combination that will then make picking the individual species pretty easy from there, right? It kind of sets up the framework, and then the detail of the individual species will just fall out quite easily for you. So what we have here on this whiteboard is 6 different scenarios, starting with a system that's bare and working through towards more complexity in the planting mix. I'm going to run through these, and ultimately it's going to highlight why, except in very specific circumstances that I'll come back to in a minute, getting down into this end with more variety of species and more complexity in the types of plants is actually the right way to go. Even though it might require a little bit more thought and a little bit more nuance up front than just being like, I'll have that, that and that off the normal list, we're going to get to that point. So, the reason why this might not apply in really specific settings with really specific aesthetic goals. So if you were putting a bioretention system into a high profile civic space like a town centre, then you might have some very specific aesthetic goals that you want to achieve that might kind of push this out of the way because you're just happy to maintain it to a really high standard and deal with some of the negative consequences from that. Because where this really came from is a conversation about how do we make maintainable bioretention systems that also perform well. So with that in mind, let's go through this. So our first scenario here is a bare bioretention system. Now that's not a good option from a treatment performance point of view. In fact, it's a very bad option because the plants are an integral part in keeping a bioretention system performing well, performing its treatment performance, keeping it draining over time, etc. So a bare system is something that we absolutely want to avoid, right? Next option here is a monoculture. So mono stands for monoculture. It's a monoculture, and this X stands for plants that are known to be poor performers. So their treatment performance has been tested and they're known to be poor performers. So clearly we don't want that option either because it's not going to do a lot of treatment good. It's worth bearing in mind here though that normally when we talk about bioretention plants that are poor treatment performers, we are talking about plants that don't do a very good job for treating nitrogen. It doesn't really imply a lot else about other pollutants that the system might treat, because while they are facilitated, and I'll talk about this in a minute, by the plants, the plant isn't necessarily isn't so directly related to it. So in the case of nitrogen, nitrogen is for a large part removed from bioretention systems by microorganisms that live on the roots of the plants. And certain species facilitate the right microorganisms, the right conditions that allow the nitrogen to be removed, and other species do not. So when we talk about species that are good for treatment performance, we're normally talking about nitrogen treatment performance. You can have a species that's terrible for nitrogen treatment performance, but by the very nature of the fact that it's a plant in a bioretention system, it's helping to keep it draining, and it's probably going to be doing pretty good things, therefore, for sediment and phosphorus and for metals, for example, right? So when we talk about poor performance, we mainly mean poor nitrogen performance. But we don't want that, right? It's not quite as bad as a bare system, because the bare system ultimately is at risk of clogging up and it's going to suffer for sediment and phosphorus and all the others as well. But a monoculture is not ideal. So we don't want this, right? Because it's not great either. But it has one other risk, which is because it's a monoculture, and when I say monoculture here, I'm referring to either true monocultures where the whole system is one species, or the sort of monoculture where you see where there are in fact 3 species in it, but they've been planted in clumps. So it's one species here, one there, and one there. So effectively, if one of them dies, you still get left with a giant bare patch. It's still effectively a monoculture in 3 separate parts. The problem with monocultures is that they're not resilient. So they're really susceptible to losing all their plants or large proportions of them and transitioning to a bare system. So it's got reduced treatment performance, and it's really susceptible of getting to terrible treatment performance in bare. So we don't want that. So let's now next come across to our monoculture with a question mark. And that means monocultures where we don't know the treatment performance of the plants. So that's going to be very similar to the monocultures of poor performers, with the bonus that we might accidentally put in something that performs really well for nitrogen removal, right? So we get left here, treatment performance is questionable, so it's not really, we don't really want it there, but because it's a monoculture, it still has the risk of going back to bare, so that's not a great outcome either, right? Then we come across to here, to our next option, which is monocultures with a tick. What that means is monocultures where the plants are known to be good treatment performers. So this would be example if you made a monoculture of carex in a system, right? So that is going to get really good treatment performance, which we like. But again, because it's a monoculture, it has a high risk of reverting to bare. So there's a high risk of turning back into this bare system and ultimately not doing good treatment. So it's a very fragile system. While it's working, it could be good, but when it's not, it's going to go bad, like both of the other monoculture options. So it's inherently fragile, and that's not good from a maintenance point of view, because fragile means risk of having to spend a lot of money. So we don't like this option either. I will give it a tick for the fact that it does performance, but we're ultimately going to give it a cross, because from a maintenance point of view, it's fragile. You can have the best system in the world, but if it doesn't stay the best system in the world, what does it matter, right? It's like the best, we're going to a movement point of view here, it's like the person who is the best athlete in their early years when they're first drafted into the AFL or the NBA or whatever sport you might be interested in. And they're absolutely great, but they're injury prone, and so they never play more than 3 games a season. That person doesn't become a star. They can be the #1 draft pick, they can be the absolute star in college or in lower grades, but if they're injury prone, they're no one. They're a bare bioretention system. That, for all its shininess and all the, oh my goodness, the carex should do great treatment performance, that is that waiting to happen. It's risky. So then we come on to our final 2 options here. This one is what I'm terming an ecosystem. So this is a system where we've deliberately planted multiple different species mixed together of multiple different types. So we're trying to mimic, though not necessarily create, but mimic the way a natural ecosystem would work. I have grouped 2 things together, an X and a question mark. It means it could either be systems with poor performing plants, so it could be an ecosystem with lots of different species, but they all happen to be poor performers, or it could be an ecosystem with lots of different species, and we don't know what they are. What's critical to understand here is that, 1, this is going to be much more resilient because it doesn't suffer from the risks of monocultures, right? So there's very little risk of this ever reverting back to bare. The worst case scenario that we can have here from a treatment point of view is that all the plants turn out to be poor performers, and the system performs no better than its best treatment performing plant. So it doesn't do particularly well. Although, of course, if we don't know about this, if we're putting lots of different species in, we could just stumble across a good treatment performance plant, and it could do really well, right? So we have a system that can never fail, that's unlikely, to fail all the way to bare. So it's unlikely to fail the way the monocultures are. But it might not perform much better than this monoculture here, right? So it's kind of locked us into a resiliency of not being any worse than this. But the thing is, it could be better because there's something about bioretention plant research that's often overlooked. The majority of the research into bioretention plant performance has focused on assessing the performance of plant species individually. So it's, okay, how does this system do? How does this lab scale system do when it's got that species in it, or that species, or that species? What's not very well accounted for is interactions between species. So when we talk about, this really good treatment performing plant, what we're talking about is this really good treatment performing plant in isolation. We're not understanding, or we're not generally talking about, or have any knowledge of, how multiple species interact with each other in an ecosystem. It's entirely plausible that when you put several species together that don't, on their own, do particularly good treatment, that you could put them together and through symbiotic relationships, they actually do better. The whole is greater than the sum of the parts, effectively. We have no understanding of that. So this system here is very unlikely to get down to this bare system, right? So all of these three previous monocultures have a very high chance of coming here unless you spend a lot of maintenance dollars on them. This system is very unlikely to go that far down. Worst case scenario, it gets down to here, but it's actually got a chance that it ends up here, right? So you can see how this is fundamentally a more resilient system, and it doesn't require as much maintenance to get there. Yes, it might end up here, and yes, theoretically, you could spend huge amounts of dollars and lock in all your systems here. But if you don't have lots of dollars, you're going there and potentially still spending a fair bit of money in the process, right? If you ever try and bring systems back up. So it's not particularly on. This, on the other hand, don't have to spend a lot of money on. Worst case, it goes there. Best case, it actually ends up performing as well as the best case monoculture. You see? Far more resilient. The final option right over the other side is an ecosystem with a tick. So lots of different plant species, and we know they're all good performers, and we know that they all perform well in terms of their interactions together. The simple answer is the research isn't here to tell us that. Yes, theoretically, we could pick a bunch of plant species that have been tested and known to perform well, and then put them together in a system. But we really, the reality is, there have been so few species tested, say in Australia, so few native species tested compared to the grand total of possible species to put in all the different climates around the country, that if you're trying to build an ecosystem that is relevant or like locally appropriate using local species, which you probably should be doing, then it's highly likely that you're going to be picking species that haven't been tested. That's the most likely scenario you're going to be picking from then. And so this is the likely one. So pie in the sky at some point down the future, it would be lovely to have all of the information, know all the perfect species, and then be able to put those into an ecosystem. We don't know that there. And so therefore, the scenario that under this framework we should be operating in is this one here, this one there. We're trying to create an ecosystem, multiple layers of vegetation, multiple different species types, thinking about succession over time. So, okay, I'm going to put these species in now because they'll get quick cover, but maybe they're not the ones I want there long term. Maybe I then want these other species to come through later, and picking the planting mix that will allow that to happen. Once you have that framework, then you kind of have some tick boxes as well. I'm going to need some early pioneer species. I'm going to need some things that are going to live longer. I'm going to be thinking about understory and canopy and even some mid-story, right? But now we have a framework that we can tick off on. We can go, okay, I need to put things into all those boxes I just mentioned, and I just need to think about how they might change over time. And that puts us in a pretty good position. You can start filling out plant species from there. Yeah, the first time you do it right, you're going to have to put a bit of thought into it. Once you've done it just a couple of times, it's going to be pretty much as easy as coming through the normal list of species and being like, I'll have 100 juncus and 300 carex, and they'll go in that blob and that blob, and I'm going to have 1 million lomandras because that's what we do. Okay, anyway, I hope that framework's useful. It was fun for me coming back into the water space for just a little bit, but I will now end this episode and resume my life in human movement gym world. Do go check out ideanthromovement.com. Have a good one. I'll see you at some point in the indefinite future.
Before you go, our best episodes come from your questions. This knowledge base, these discussions that are Ideanthro improve with your contribution. So if there's a topic, an idea, a concept that you would like us to explore, come and ask us. You know where to find us. www.ideanthro.com/contact. You can find us on Facebook, YouTube, LinkedIn, and that place you get your good podcasts from. You know where to find us. We look forward to hearing from you. We'll see you soon.